So our next topic is a simple linear regression analysis. And we are going to start by defining two variables, y and x. We define two variables, y and x, which we are calling observable variables. Then a simple linear regression equation can be defined as shown in equation number 5. So when you have an equation like the one given in number 5, it means that we are predicting y using x. We are predicting y using x. So there is causality, as explained earlier on, is only x that can predict y, but not the vice versa. So the simple linear regression model is given as up here, okay, where y is called the dependent variable. Is called the dependent variable, and there are other names that can also be used to define y. So you can also call it the explained variable. So it's called the dependent variable, the explained variable, the response variable, the predicted variable, or the regressant. So all those names refer to the variable being predicted. Then we have x. X in this case is called the independent variable. It's also known as the explanatory variable or the control variable. Sometimes you also call it the predictor or the regressor. So those are the names of the variables. So in this case, this is the independent variable. And in this case, this is the dependent variable, okay? Then we have the constants, beta naught and beta 1. This is beta naught and beta 1. Those two are called the regression coefficients. And the regression coefficients are always unknown. They are population parameters. They are population parameters, and they are always unknown, just like all the other parameters. They are always unknown. So when you say that a parameter is unknown, what should cross your mind is that at some point we may be required to estimate it, and you estimate it using sample information. So at some point we'll need some sample data on y and some sample data on x. Then we should be able to estimate the values of beta naught or beta 1, okay? Then the last term there, ui is called the error term. So this is called the error term. It's called the error term. Some people prefer to call it residual, okay? Actually, some people prefer the word residual than the word error term. Huh? So when you talk about a residual, it's the effect, it's the variation. The residual here is the variation in y, which has not been captured by, or which has not been explained by the given independent variable. For instance, if you look at, if you have something like initially we had consumption. We had consumption and wealth. So if you try to predict consumption using wealth, maybe you'll have an equation like this, plus beta 1, wealth plus some error term there. I think it is easy to know that wealth may not explain all the variation in consumption. There are many other factors that also affect consumption, not necessarily wealth. So wealth is not enough. Chances are very high that there are many other factors which are affecting consumption, but they are not in the model, because in the model we only have data about wealth. So all the effect of all those other factors is plugged in here. The effect of all those other factors is captured in the error term or in the residual. Okay, so if you are trying to explain consumption and then you are using W only, then clearly you may want to make this error term as inconsequential as possible, because you don't want to predict a consumption using wealth when the most important factors are actually captured here. So you may want to include all the possible factors in the model or you make sure that you only have the most important variable here. You only have the most important variable there. Okay, so we'll be looking at that a little bit later. So the error term is our U, and the error term is of great focus when we come to regression analysis. Okay, that part is very important in the regression analysis, especially the behavior of the error term is core in regression analysis. Okay, so we're saying that it is a combination of several effects, or it's a combination of several factors, such as if there are some variables, explanatory variables, that have been omitted in the model. If there are some variables that you've not captured in the model, they'll be lumped up. Their effect will be lumped up in the error term. Like in that example I've just given there, if you're only predicting consumption using wealth, then the effect of all the other variables that actually affect consumption is captured under the error term. Okay, so those are omitted variables. Okay, then we also have the error term capturing non-linearities. Okay, so for instance, if your model looks like this, consumption is equal to beta naught plus beta 1 of wealth plus the error term. This is a linear model. Okay, so you are assuming that there's a linear relationship between C and W. That may not be the case. You may find that in the actual sense, the true relationship between consumption and wealth is something like that. So you find that instead of fitting a quadratic model, you fitted a linear model. So in that case, the effect that would have been covered or captured by W squared is lumped up again in the error term. And so you will find that now the error term has some relationship with W, because there's some effect of W which has been lumped up in the error term because it was not well captured. Or maybe you needed to fit a cubic model like that. Or maybe you needed something like this. Sometimes you may have something like this: beta naught plus beta 1 W raised to power half. So maybe that is the correct version of W that will predict consumption more accurately. So all those non-linearities are captured in the error term. Okay, so, and we are given an example. For instance, if the true model is given by this, which is a quadratic model, as you can see, the highest term of X is that. So the highest power of, the lowest power of X does not matter here. So even if this term was not there, it will still be quadratic. Huh? So if this is the true model, where the error term here is called ZI, but we wrongly assume that Y has a linear relationship with X. We wrongly assume a linear model like this one here. Then you see this term here has been omitted. So the effect of X squared is absorbed in the error term. So the effect of X squared, which is missing here, goes here. So that implies that your error term now, your error term looks like this. Your error term looks like this, which is a systematic. So here, your error term is a systematic component here, which is quadratic. So your error, if you plot the errors, you will get something either like this. The errors will form something like that, which is not something that we may want to observe, or maybe something like that, quadratic. So your error term will be looking like that, which is a very bad signal. You'll see that later. Okay, then the error term can also capture what we call measurement and observational errors. Remember we said that the data that we use here is observational data. Now, data which is observational is not controlled for measurement and observational errors. So you can get errors out of, because of the tools that we're using to measure the variables in question. So the inaccuracy of the tools that we're using to capture the data will bring about what we call the measurement errors or the observational errors. Okay, so all those inconsistencies of the observed data from the true values, is also captured under the error term. It's also captured under the error term. Then finally, the error term also captures random effects or random errors. So where these are uncontrollable discrepancies between the observed and the true value. So I want you to differentiate between measurement error and the random errors. The measurement error is because of the tools or maybe the biases that are accompany, or the mistakes that accompany recording and capturing of the data. But there are some other errors which are not observable, which are very random, which are inherent in every process, and cannot be controlled. So all those effects are also captured here. So an ideal model is one where the error term, an ideal model which we'll never achieve, is a model where the error term only comprises of this. If you can get a model that only comprises of that, there are no measurement errors, there are no non-linearities, there are no omitted variables, then you'll have a very good model. It is very unlikely for you to have that. So what we do, we really want to minimize this term here. Our objective is always to minimize the error term. Minimize the error term there. Okay, so how do we get about that? So in order to make sure that the error term is inconsequent in our regression analysis, then we use several methods in the estimation of the parameters. We use several methods in the estimation of parameters. And the method that we're going to discuss here is what we call the ordinary least squares method. Ordinary least squares method, or the Ols method. Now this method is very simple to explain or to understand. So usually you start with a scatter plot. When you have we have two variables, you have your y and then you have your x variable there. So you have a scatter plot. There's a message from someone. Did someone write a message? I think there's no message. Yeah?
Yes, there is somebody who is waiting.
All right, all right. All right, I've seen, thanks. So when you collect your data, X and Y, the starting point usually is to come up with a scatter plot. So let's say these are my points. Let me use color red. So these are my points. I'm choosing a very simple, a very small data set. So that's what I'm calling my scatter plot. Usually the scatter plot is a starting point even for regression analysis. So if you want to fit a good model to predict Y using X, we need to fit a straight line here. We need to fit a straight line here, which best describes this kind of relationship. Now, using the Ols method, we can estimate the values of beta naught and beta 1 in such a way that if we put the line here, that's just a random, I've just placed it anywhere. So we need to put a line somewhere in between the points in such a way that if you measure these distances here, if you measure these distances, I'm calling them E for errors. I can call this one error 1, error 2. You measure all those vertical distances, error 4, error 5, vertical distances, error 6, error 7, error 8. Let's say I only have 9 points, so error 9. So the best line that describes the relationship between Y and X is a line drawn through the points in such a way that if you take these errors, then you square them, so I'm calling them EI, then you square them, that summation here, if you sum the square of the errors is minimum, is as small as possible. The sum of square of the errors is as small as possible. Then you will end up, if that happens, you will end up with a line which you usually call a line of best fit. You will end up with a line which you usually call a line of best fit. So this line is a line of best fit if the summation of the errors squared is at the minimum. You cannot get any other smaller value of squared errors. So that means that if you draw any other line there, it's true you'll get errors, but if you try to square these errors and then you sum, then that will not be the minimum error. That will not be the minimum of the squared error, sum of squared errors. So there is only one line, which is a known, which will pass through the points, and that will minimize this kind of expression. Now that process of minimizing the sum of square of the errors is what we call the ordinary least squares method. The word least there means minimum. Least squares. Square of what? Square of the errors as shown here. So that's what you're calling the Ols method. Now the derivation of the coefficients will be, I've shared a video. I don't know whether some of you have seen it. So we'll be checking the video. So here we'll just be looking at the assumptions and maybe some simple derivations to support what is captured in the video. So we're saying that given observations X and Y, where Xi and Yi, where I is ranging from 1 to n. So this just tells us the size of the sample. So here we should visualize something like this. We should visualize something like this, where you have X and Y. So here you have X1, X2, all the way to Xn. So that's why I'm saying Xi, where I starts from 1 all the way to n. So this is actually the size of the sample size. And Y also, we have Y1, Y2, all the way to Yn. So let's consider something like this. So we have something like this. That's what you should visualize, okay? Then the task of an econometrician is to estimate the population parameters. So our task here will be to estimate the values of beta naught and beta 1. And the value of beta naught is the intercept, parameter. And then beta 1 is the slope parameter, the gradient of the above equation. So remember the scatter plot that I've just removed from here will be fitting a line possibly looking like that. And then we have the points like that. So this point here is what we are calling beta naught. Beta naught. And we are saying that point is unknown. You cannot just get it by speculating. You cannot just locate it using the scatter plot. It may not be easy for you. Then beta 1 is the slope of this line. And we know the slope is given by some change in y, change in x. So the slope is some change in y over change in x. That's the gradient. That's the basic definition of gradient. So this is what will give us the value of beta 1. That's what will give us the value of beta 1. And you see, you may not know, that is not something that you may not know without doing some estimation or calculation there, okay? Okay, so we need to estimate the values of beta naught and beta 1 in such a way that, in an optimal way, and an optimal way is what I've just explained, in such a way that if you measure those errors, you square them, then you sum, then you're going to get a very small value. You're going to get the smallest value possible. So there's only one such line that will minimize the sum of square due to errors. And that line is what I mentioned earlier called I called it the line of best fit, the line of best fit. Now there are some assumptions that I want us to mention. There's some assumptions of the Ols model, and usually they are called the classical assumptions. Number one is that the error term has a mean of 0. The error term has a mean of 0. The mean is called the expected value in the context of probabilities. So the expected value of the error term, remember the error term is u. So this here means the expected value. expected value means is the same as the mean value. The mean of the error term. So just like I've said here, the mean of the error term is equal to 0. And I guess we know how to find the mean of something. Yeah? So if you sum up all these values and then you divide by the number of observations, you're going to get 0. And when do you usually get the mean is equal to 0? Remember, the definition of mean is very simple. Huh? So we know that mean is equal to sum of all the observations divided by n. Remember, our sample is of size n. So when can this one be 0? When can this be 0? We can only get the mean is 0 if the sum of all the observations here is 0. So that means we expect that the sum of all the errors should be equal to 0. Usually, when you talk about 0 here, it may not be 0 actually, but should be something very, very close to 0. So it should be something very, very close to 0. So that when you divide by n, you also get something which is not very different from 0. So that's the first assumption. But the ideal situation is when you sum and you get the actual value 0. Okay. Number 2, as you can see, the assumptions are revolving around the error term because we want the error term to behave in a certain way so that we can make a conclusion that our model is good, or we can make a conclusion about our model, whether it's good or it's not good, whether it can be improved or it's okay the way it is, things like that. Okay. So assumption number 2 is slightly technical. We're saying that the error term is homoscedastic. Homoscedasticity, that's the other word, okay? And homoscedasticity here is a question about the behavior of the variance. It's a question about the variance of the error term and especially the behavior of the error term. Now, when we talk about homoscedastic, the opposite is called heteroscedastic. Heteroscedastic. So that's the opposite of that. When you talk about homoscedastic, I've given a mathematical definition. I don't know whether some of you will appreciate it. We're saying that the variance of UI, the variance of the error term is equal to sigma squared. A better way of saying that is that the variance of the error term, is constant. Is constant. So when you talk about the variance, you know, variance is a measure of spread, is a measure of dispersion. So I want to sketch that so that you see what is meant by homoscedastic, and you'll also be able to see what is heteroscedastic. Though the details about that homoscedasticity and heteroscedasticity are captured in some other topic. So if you plot the error terms there, if this is if these are the individuals, remember we have n of them from number 1 all the way to n, then you have the error term. We have the error term on the vertical axis. Then for individual 1, you plot the error. Individual 2, you plot the error like that. You'll find that your errors will be something like that. For every individual, you have an error. So when we talk about homoscedastic, we mean that it should be constant. That is, if you are to draw a band like that, the error term should remain constant like that. Should remain constant like that. Should form a horizontal band like that. Now, if that is violated, you may have something like this. Let me use color green, color blue. If that is violated, you may have something like that. You may have something like that. So you find that the error term is not constant, but is increasing as you increase these IDs, as you move from one individual to other. So you find that you form a cone-shaped band like that. So this one signifies The blue one signifies heteroscedastic. The error term there is heteroscedastic. But in the red one, here we say that the error term is homoscedastic. So the assumption here is that the error term remains constant throughout for all the individuals. It's the same. It remains constant for all the individuals. Okay? So we'll be looking at those details a little bit later. Okay? Now, the next point or the next assumption is about the independence of the errors. Actually, point number 3 just says that the error terms, the error term should be independent, or the errors are uncorrelated, or the errors are independent. That's why we're saying that the correlation between any two individual errors, the correlation between any two individual errors. So when we have the correlation of UI and UJ, UI, this is one individual, this is another individual, the error of one individual, the error of individual I, and the error corresponding to individual J, we are saying that those two should not be correlated, And that is for all the individuals in the data set. For all the individuals, there should not be any correlation between the error terms, between the errors. Then for technical purposes, we are saying that if you take this deviation squared, if you take x minus x bar, you square, then you sum, then that should give you a positive value. Some of you may notice that if you are defining standard deviation of x, the formula is, let's say variance. Let's call it variance. If you want to define variance of x, this is given by summation of x minus x bar divided by n. That's one way of writing variance. So we are saying that this numerator here should be positive. Should be positive. You will see why a little bit later when we come to the estimation of beta 1. You will see that it should be coming at the denominator. This term here will be the denominator of our estimate for beta 1. And we do not want a denominator which is 0 or something like that. And maybe if you want to get the standard deviation, we may want to get a square root. Okay, and we don't want to get a square root of a number which is not positive. Okay, so then finally, number 5 assumption is that the error term is not correlated with the explanatory variable x. The error term is not correlated with the explanatory variable x. So that points to our if you look at what we said here about number 2 here, non-linearities. Okay, so if some variables are, sorry, number 1 and number 2 actually. So let's talk about number 2. Let's talk about number 2. If, for instance, this term was omitted, if this term was omitted in your model, then you may find that your error term here has some relationship with x. You may find that there's some relationship between x and the error term. So that's what we are trying to avoid by having that kind of assumption there. Okay, so we're saying that the covariance is equal to 0 because we know correlation. How do you define correlation? Correlation of x and y is given by the covariance of x and y divided by the standard deviation of x multiplied by the standard deviation of y. And this correlation can only be 0 if the numerator is 0. Correlation can only be 0 if the numerator is 0. So if this is 0, it doesn't matter whatever is here, it will also be 0. So that's what we're saying there. That's what we're saying there. Okay, so there are some notes here. I think I must have mentioned them. Is that assumption 1 and 2 are related to the distributional properties of the error term, of which assumption 1 can always be fulfilled when the intercept beta naught is included in the model. Then assumption number 2 will be discussed a little bit later about homoscedasticity and so on and so forth. Then the second note is that assumption number 3 is most relevant in time series data, or what you call sometimes cluster data. So assumption number 3, which is autocorrelated, is uncorrelated. We find that in most of the cases, when we're using data which is not which is not time series or panel data, this problem number 3 is not persistent. It's not persistent, okay? But when you have time series, it is one of the problems that you must solve. When you have time series and panel data, it is one of the challenges that you have to deal with because the error terms are always correlated. A good example is when you look at stock prices, you notice that the closing price today usually is dependent on the closing price yesterday. So you find that the error term for today is very much related to the error term for yesterday. So that's what you're calling the error terms are correlated in such a case. For time series, that is inherent in the process, and error terms are always correlated. But when you are dealing with cross-sectional data, that problem is not persistent. That problem is not persistent. And when it comes, it is usually very easy to sort out. Then assumption number 5 is the key assumption on how X and U are related. We're saying that sometimes it is expressed in stronger terms, in stronger assumption of mean independence, okay, as shown here. So this is a definition of mean independence, okay? I guess you know what the meaning of independence. You say that two events, A and B, are said to be independent if let's say probability of A given that B has occurred is equal to probability of A. Okay, so if U and X are independent, then we are saying that the value of UI given the error term is just UI. So that means that UI is not in any way dependent on X. UI is not in any way dependent on X because this means given that. So the value of the error given the values of X is equal to U, is just equal to the value of error. Then once you introduce the expected value, which is the mean value, you also get like that. So the mean value of the error term given X is the same as just the mean value when you ignore X, okay? So that's the other way of defining assumption number 5 in what you're calling stronger terms. Now, as I mentioned a little bit earlier, the goal of the Ols method is to minimize the sum of square due to the errors. You minimize the sum of square due to the errors. So let's consider model 5. Model 5 is called the population regression function. Model 5, which is defined a little bit earlier there, it looks like this: yi is equal to beta naught plus beta 1 xi plus ui. That's model 5. Okay, so that's what we are calling the population regression function, and it can be estimated because as we know, the values of beta naught and beta 1 are regression parameters. Okay, and they are known, so we can only estimate it. So we can estimate that model using this function number 6. So you find that we're using the same terms, but now we're introducing the hat. Okay, we're introducing the hat. The hat here is used to signify estimate. So beta naught hat is the estimate of beta naught. Beta 1 hat is the estimate of beta 1. Then ui hat is the estimate of the error term, and so on and so forth. So we can estimate that model using equation number 6. Using equation number 6 there. Okay. Then we say that for given values of X, if now you collect some data then the estimated value of Y is given by this equation number 7. So now you express the model in this format now. So you even have Y hat, the estimate of Y is equal to the estimate of beta plus the estimate of beta 1 multiplied by the observed values of X. Observed values of X. So this is the data, the actual data. And you notice that in number 7, the error term is not captured because the error term is unobservable. You cannot observe it, okay? So this is now called the sample regression function. It is called the sample regression function because it's based on sample information, okay? Or sometimes you can call it the fitted line. Sometimes you can call it the fitted line, okay? Then I think there's an error in my notes here. The reference I've given here is not correct. So from equation 6 and 7, if you use equation 6 and 7, not 2 and 3, this one should be 6 and 7. The error term. So now using this equation and this one, we're able to estimate the error term also. Because as you can see, the error term is the guy which is omitted there. So we can say that the error term is given by yi minus yi hat. So just find the difference between, you just take equation 6 minus equation 5. So my equation 7. So that difference is what gives you the error term, because as you can see, this will go with that. This will go with that. Then you'll have yi minus yi hat is equal to the error term. Is equal to the error term. So you have that. That's the error term. That's what I was initially calling the EI. So now it will be something like that. So which you can write in this format. So that's our error term given by that. Remember I said the objective of the OLS method is to minimize the sum of square. If you square this, then you sum. So that means you take like this. And that means you also do the same on the right-hand side. So if you're able to get a minimum value, then the beta naught and beta 1 that correspond to those errors will give you the line of best fit. So we're saying that under the above classical assumptions, the OLS minimizes the sum of square due to the residues, or some people will call it the sum of square due to errors. So, but in this class, I'll be using the word residues, not errors. Residues. So they'll denote it as SSE instead of SSR. So please don't get confused sometimes. So we want to minimize the sum of square due to the residues or the errors. Okay, and because we already have defined the error term above there, this is what we are trying to do. Sum of square due to the errors. Then on the right hand side, we also have the summation of the right hand side, but now when it is squared. We want to minimize this function. We want to minimize that function. So for simplicity, I have replaced the item on the left hand side with the letter S. Then on the right hand side, I have this. So I want to minimize this function. If you minimize that function, you will be able to get the values of beta and the values, you'll get a formula for the values of beta and beta 1. Okay, so, and as you know, minimization of functions is done through differentiation. So we need to differentiate a function for you to get to locate the minimum point, and there's a process of obtaining the minimum point. So there are some two conditions that must be satisfied for you to be certain or to be sure that you have obtained the minimum point, because you don't want a scenario where the function looks like this. You don't want a scenario where if this is the function, you don't want a scenario where you are obtaining this point, you are confusing this point to be the minimum point. You don't want a situation where that is true. You want a situation where it is confirmed that this is a minimum point here. And there are two conditions that must be satisfied for any given point on a function to be the minimum point. And generally they are called the first order and the second order condition. So the first order condition means that the first derivative of the given function, if you differentiate this function just once, the first derivative is equal to 0. The first derivative is equal to 0. That just means that the gradient of that function at that particular point is equal to 0. The gradient is 0. And the gradient can only be 0 if you have a horizontal line. So you notice that if you confuse this other point here to be the minimum point, if you draw a tangent to this point here, it will not be a horizontal line. So that's not that will not give you a gradient of 0. So there's only one point. There's only one point on this function that will give you a gradient of 0, and that is the turning point here. So you must be at a turning point. You must be at a turning point. That's the point where the first derivative, which is the gradient of the tangent, is equal to 0. The tangent to the curve at that particular point is equal to 0. So that is true even for maximum turning point. So if your function looks like that, then this turning point here will also have a gradient of 0. So the first derivative is equal to 0 for both a maximum turning point and a minimum turning point. So to differentiate between a maximum and minimum turning point, you need to perform a second derivative. And that's what will satisfy the second order condition. And the second derivative of the same function. So you differentiate this, this function twice successively. So if it's a minimum point, the first condition has been satisfied. So if it's a minimum turning point, then the second derivative should be a positive number. The second derivative should be a positive number. But if it's a maximum turning point, the second derivative should be a negative number. Should be a negative number. So we have to differentiate this function. For the first time, you equate to 0. Then for the second time, then you confirm that the value that you are getting is actually a positive number. That will confirm to you that you have a minimum, you have minimized S. You have minimized S. Okay. So the first order, which is a partial derivative, is partial because this function here, this is a function. So we're dealing with a function of beta naught and beta 1. So the function in question is a function of beta naught and beta 1, which are linear. So we are differentiating first with respect to beta naught, then we differentiate with respect to beta 1. Those are partial derivatives. So you differentiate with respect to beta naught when you are holding a beta 1 constant. When you're holding beta 1 constant, you equate that to 0. And here you're going to use what we call the chain rule of differentiation. It is shown in the video, so I'll not go to much the details. But you will notice that when you talk about the chain rule, it is quite simple, because what you just need to do here is to let the guy in brackets here to be u. You let the guy in brackets here to be u. So let me give you, let me illustrate that using a simpler function like this one. If you have y is equal to, let's say, x cubed plus 3x plus 4 power 7, and you want to differentiate this kind of function, you find that it may not be possible for you to expand this item to power 7. So that would be very complicated. It takes you a lot of time. So if you want to differentiate this is not partial derivative. So you will let the guy in bracket here to be u. So you let u to be equal to x cubed plus 3x plus a 4. So that means you can redefine your y into u power 7. You can redefine it into that format. Okay. So now what you do, you now differentiate, you differentiate this guy du with respect to x, which is a very simple derivative, which will be 3x squared plus 3 plus 0, like that. Okay. Then again, after that, now you can differentiate y. If you differentiate y with respect to u, so you want to differentiate this with respect to u, that would be quite simple. This would be 7 u power 6. Okay. Then the derivative of y, remember we're looking for dy dx. This will be given by dy du multiplied by du dx. So you just need to get a product of those two. So let me write it here. So this is a concept that will be applied here in this kind of differentiation. So dy du, we already have that is here. So this will be equal to, 7u power 6. Then I multiply that with du dx, and du dx is this item here. So this will be 3x squared plus 3. Okay, so that's the derivative. But you may want to replace this guy here with the actual value of u here. So this will be the same as 7. Then you have x cubed plus 3x plus 4 raised to power 6 multiplied by you plug in this guy here now. So that is it. That's what we call the chain rule. So that's basically what we shall be doing here, or what has actually happened here, as shown here, and also as you will see in the video if you have not watched the video. Okay, so the derivative with respect to beta naught, you will get this equation here, which you must set equal to 0. So you will get this. I guess you'll know that this one was this 2 was the power, because already you let this guy here to be u. So this is your u. So you have your y is equal to u summation of u power 2. Okay, and so on and so forth, where u is this guy. Then you differentiate with respect to beta 1. You differentiate with respect to beta 1, and you get this equation here. You get equation number 10. Again, you also equate to 0. So the first derivative is equated to 0 in all the cases. That's the first order condition. Okay, then you can simplify this. And we'll end up with equation 11 and 12. And equation 11 and 12 are quite familiar, I think, to almost all of you. If you open the brackets and you try to simplify, you obtain equation 11 and 10. 11 and 10 are very familiar equations. Let me set this one. Let me remain with this one on the left-hand side. So let me take all these to this side. So that means I'll have my equal sign there. Then this will be a plus. Then I remove this. Which equation is that? Which equation is that? This is what we have. We have summation of y is equal to n beta naught estimate plus beta 1 summation of x. What is that? And the second equation is summation of xy is equal to beta naught summation of x plus beta 1 summation of x squared. These two are what we call normal equation in statistics 1. In statistics 2, sorry. These are what you call the normal equations. So in the previous class, we were just stating this and solving them, and solving them simultaneously to obtain the values of beta naught and beta 1. So the normal equations are actually coming out of this process, the process of trying to minimize the sum of squared due to the errors. So those are the normal equations, which can be, sorry, before we simplify that, we can also have, just a minute, somebody's calling me. So we can check, that was the first order condition. We can check the second order condition. So that means we do 2 successive derivatives of each one of them with respect to beta naught and also with respect to beta 1. So when you do 2 successive differentiations with respect to beta naught, so the next step is to check the second order conditions. And as I've already mentioned, is that we do successive differentiations with respect to each of the regression parameters. And when you do successive differentiation using with respect to beta naught, you will get this value here, -2 times a -1, which is a positive number, which is 2, is positive number. Okay. Then that should also be true. You should also get a positive number when you do 2 successive differentiations using, with respect to beta 1. So if you do that, you'll notice that the answer will be something like this, where the negatives will cancel, and then you'll end up with a positive summation of x squared, positive summation. You'll get a 2, then summation of x squared. Clearly this is positive, and there's no way this one can be negative. There's no way that part can be negative, because when you square a number, you are likely to get, actually you will get a positive number or a negative value in that case. Okay, so that means that condition 2 has been satisfied. As you can see, through OLS, we have satisfied the 2 conditions, and clearly we have minimized the function S. Okay, so then we are saying now we just need to play around. We just need to play around with Joseph Mbondi. Your hand is up. Joseph, do you have a question? Okay, so I was saying that you just need to play around with equation 11 and 12. And then you make beta naught the subject of the formula as well as beta 1. Usually when you have actual data, you just solve these 2 equations simultaneously. You just solve them simultaneously. And when you solve them simultaneously, you'll be able to get the values of beta naught and beta 1. So through some algebra, once you manipulate those 2 equations, you will end up with beta naught is equal to y bar minus beta 1 hat multiplied by x bar, where of course y bar and x bar are the sample means of y and x respectively. Then beta naught will be given by this equation, will be given by that equation number 16. Okay, so these ones are easy to see. Then we are saying that beta naught hat and beta 1 hat are the estimates of these 2. They are estimates of beta naught and beta 1. Then it's good for you to note that these formulas, especially number 16, can be simplified or written in another format if you let this guy, if you let the numerator there to be expressed in this format. You can write the numerator in this format, and the denominator, you can write it in this format. So that means you can write beta 1 as equal to, or beta 1 estimate can also be written as summation of xy minus n x bar y bar divided by summation of xi squared minus n x bar squared. So you can write this formula. So this is the same as number 16. It's the same. It's the same. So you just take x and y. So you find that you don't need to find so many of these things. So you just take the actual data most of the cases. Okay, then we can also express beta naught, I mean beta 1, in the form of covariance, in the form of as a ratio of covariance divided by the variance of x. Covariance of x and y divided by the variance of x. If you recall, sorry, I think I've given those things here. The covariance of y and x is given by this. Maybe a better way is to write them like this: minus x bar, y minus y bar, divided by n minus 1. That's what we are calling covariance of x and y. Okay. Then the variance of x is the mean due to the square deviation. So this will be summation of x minus x bar squared divided by n minus 1. So you notice that if you divide this by that, the divisors will go away. The values of n minus 1 will disappear. So you'll be left with summation of, we'll be left with this item on the numerator and this item on the denominator, which is similar to this, which will be similar to number 16, which will be similar to that. So you can rewrite this. You can rewrite this as in the form of variance and covariance. So beta 1 can be estimated using covariance of x and y divided by the estimated variance of x.
Excuse me?
Yes, yes.
I can say the screen is not changing.
Oh, the screen is not changing?
I don't know whether it's just on my side or it's for everyone.
Yeah, we can get someone else talking about the same. Anyone who can see, who is having a problem with the screen?
It is changing.
Yes.
It is changing.
It is changing. Huh? So
The screen is...
you want to check your internet connection. Huh? Rosogutu? Rosogutu, your hand is up. You have a question?
I'm saying it's not changing on my side.
It's not changing, but for some people it's changing. So you may want to check your internet connection. Huh? You can refresh the page. You can refresh the page. You should be able to change. Someone has written a message here. Someone has sent a message. What is the message about?
You are breaking.
Okay, I'm breaking. Is that true for everyone? Only you are breaking. That's
No,
right.
not really.
Somebody is asking me to repeat chain rule, Lillian. Okay, all right. So do I need to repeat chain rule? Huh? We can just go back there briefly. And I will not illustrate using this complex example. I will illustrate a chain rule. Let me just illustrate from where I am. Huh? So I illustrate chain rule using a simple example like the one I showed you there, so that now you can use that idea even in this case. So the chain rule is one of the rules of differentiation. And I had given a function like this. If y is equal to x cubed plus, let's say x power 7, and let's say x power 8 plus x power 6 plus 3 squared x plus a 1 power 8, if that is your y, if that is your value of y, and you want to find dy with respect to x, usually you find that you have the option of expanding this thing to power 8, which can take you a very long time unnecessarily. So to avoid that, using the chain rule, you let the part in brackets to be your u. Let u be the part in brackets, so 3x power 8 plus 5x power 6 plus 3x squared plus x plus a 1. So that's your u. Okay, so that means that your y is equal to u power 8. I hope we are there. So then from there, the chain rule is defined as follows: dy with respect to x, which is what we are looking for, is given by dy with respect to u multiplied by du with respect to x. That's the chain rule. So you just need to obtain these two derivatives. So from here, I can get dy with respect to u, which is going to be 8u power 7. Then using this function here, I can get derivative of u with respect to x. So that will be du dx, which will be equal to, I just differentiate this, each of the terms. So this will be now 24x power 7 plus what? Plus 30x power 5 plus what is this? Plus 6x power 1 plus a 1 plus a 0. So now the derivative, the required derivative will be this times this. That is this times that. So I multiply those two. And if I multiply those two, I'll get my dy dx as equal to 8u power 7 multiplied by 24x power 7 plus 30x power 5 plus 6x, is it so? Yeah, plus a 1. But now you may want to leave the entire answer in form of so you can replace this term here u with this item here, because u is this. So you can copy all this and put it here. So you'll end up with 8. Then you have 3x power 8 plus 5x power 6 plus 3x power 2 plus x plus a 1 power what? Power 7. Then you have this 24x power 7 plus 30x power 5 plus 6x plus a 1. Okay, so that would be the derivative of the given function. That would be the derivative of the given function. Is that okay? Is that okay, Ross? Was it Ross or what was the name? So that's the chain rule. So that's the concept you will apply here, and it has also been illustrated in the video that I'm talking about. The video has been posted on Moodle, I think, since last week. So you should have checked it, or you should just check it. Okay, Victoria, Mwinzi.
Mwalimu, I have a small concern.
Yes, yes.
Can we use a whiteboard instead when you're writing on top of the notes?
Yes.
Unapata, I am somehow missing some parts. I'm
Yes.
requesting if you can use a whiteboard kindly when you're giving the explanations.
That's perfect. That's okay.
Okay, thanks.
All right. So, but I don't need to repeat the bit on chain rule using the whiteboard, or do I?
You don't have to.
I don't have to. Thank you. Yes, somebody is saying I have to. Sorry, I can't hear clearly. You're saying?
No need of
All
repeating.
right. Thank you. Thank you for that. Okay. Thank you for that. So now let's proceed. So we're saying that you can express beta naught in these two different ways, and so on and so forth. Okay. Then sometimes you can also express beta naught in this format. So let me switch to the whiteboard. Let me switch to the whiteboard. So that's what we said, beta naught. We said that, let me repeat a bit of what I've said, is that we can also write beta 1, these are estimate, as equal to the covariance x and y, which is an estimate of the same divided by the variance of x. Because we know that the covariance of xy is given by summation of x minus x bar multiplied by y minus y bar divided by n minus 1. And the variance of x is given by summation of x minus x bar squared divided by n minus 1. Okay, so this is what gives out that formula. And we're saying that we can also express it differently. Oh, this is beta 1. We're saying that we can also express beta 1 in the form of using correlation now. And sorry, this is the same thing. So this is the same thing. So this is just the same thing. This is just s of xy over s of x, where the numerator is just the covariance. S of xy is the covariance between x and y, and then the variance usually is a square. So the covariance of x and y and the variance of x. So this is just another denotation of the same thing there. Then maybe this is what I thought we are going to explain. You can also express this in terms of correlation. You can also express this in terms of correlation, where you have something like this. So this is just a little bit manipulation of this expression. When you manipulate this a little bit, you'll end up with the formula given there. So from this, let me switch to this place. So when you have beta 1 estimate is equal to s xy over s x squared, you can play around with this kind of expression. You can play around with this kind of expression. Let's say, suppose you multiply, if you multiply here by s of x, s of y, you multiply by those two, and you divide by the same, s of x, s of y. You notice that you will not have changed anything, isn't it? You will not have changed anything. Huh? So then after that, you can play around. You see s of x squared is the same as s of x multiplied by s of x. Okay, so I can have this one as s of xy multiplied by s of x, s of y, divided by, I want to start with this one, s of x, s of y. Then now I want to have this one later, s of x, s of x. So I can keep this one on one side. I can keep this one on one side, that one. Then I can do that. I can do that. So I'll be left with S of xy divided by S of x, S of y, multiplied by S of y over S of x. And what is this? What is this? That is actually the definition of the correlation coefficient of x and y. That is R of xy. So we can say this is the same as R of xy multiplied by S of y, S of x. So you can play around with that formula and get different versions. So if you're given the correlation coefficient, the Carl-Pearson's correlation coefficient, and then you are given now maybe I need to shed more light on this. This is the standard deviation of y, and this is the standard deviation of x. Okay. So actually what we have here, this is, if I were to write this in full, this is the covariance of x and y divided by standard deviation of x, multiply this by the standard deviation of y. And that's the correlation. This is the Carl-Pearson's correlation coefficient. So you can have different versions of the estimate for beta 1 and so on and so forth. Okay, so you can also have equation 21 there, which is doing the same job as the others. Okay, so I think the derivation has been shown and so on and so forth. All right, then we have some example here. Any questions so far? Any question? So we have some example here. And as I told you earlier, I'm using data from the textbook called Wooldridge. We're taught to consider a regression of individuals' hourly wage on the number of years of education they have completed. Okay. Then we denote the wage with denote the wage to be equal to the average hourly earnings and a duke. So this variable here and this variable here have been defined as the years of education, and the other one is the hourly, the average hourly earnings. So you have this data, but this whatever is showing here is just an extract. It's just an extract of the longer data set. Okay, so this data has 526 observations, but here I've only shown 6. These are just 6 individuals. 6 individuals.
Excuse me.
Yes.
Oh, someone is waiting to be admitted.
All right.
Thanks.
All right. So we're saying that what we have displayed here are just 6 individuals out of the 526 individuals. Okay. So this is the data in question. So the data is called wage.raw in the textbook. Okay. So let me display that data set. Let me display that data set in a short while. So let me repeat the bit of activating your data analysis toolkit. So as you can see, mine is displayed here. When you click the data analysis tab here on your Excel, you should be able to see this. So what I'll do, I remove mine so that we can have the same thing. So I'll go to file. I'm removing that. So then I go to options. I go to add-ins. So that's the same procedure you follow when you want to bring it to add it. And so then I uncheck this part. If you also want to deactivate yours, you uncheck that part and you say okay. So now maybe this is what most of you have. There's
Yes.
nothing here. There's nothing here. So if you want to activate the data analysis Toolpak, you go to file, you click on file, then you go down to the options. you click on the options. Then on the left panel here, you go to add in. You add in. Then you click go there. Then you'll see some options here. I hope you can see. I hope you're using the same Excel. Then you check the first one. You tick the first one, then you say okay. You say okay. So once you do that, now you can see it is there, data analysis. So this is your data analysis Toolpak now. Okay, you can perform most of the statistical analysis using this this option here. So for instance, I can repeat the regression analysis bit. If I click here, if you click there, you see several options here. Analysis tools. You can scroll from up there. The first one is ANOVA, single factor. I can I'm using my down arrow to check through what is there. There are several things here. Several things have been put here. Okay, histograms for etc. So our interest here is regression analysis. So I select regression and I say okay. Then here I input. Are you there?
Yes.
Yeah. Then now I need to input the range or the cells that contain the Y variable. You can type that manually, but it is easier when you just select. So my Y variable is wage, so I can click there. So when I click there, I press the shift key and then I press the down arrow. I press the shift key first, then I press the down arrow. So now I've pressed the shift key, but I've not pressed the down arrow. So now I just go and press the down arrow, so that I select all the cells that contain my Y variable. All of them. I'm pressing continuously. I'm pressing continuously all the way to the last cell. All the way to the last cell. Then then up to there. Then I just release like that. I've just released the shift key and the down arrow. Then without doing anything, I just come and click inside this this box here, where I'm going to input the range of the X variable. So here I'm going to capture all the cells that contain my variable X. So I'll start from up there. You can also start from down, it doesn't matter. So I start from up there. So I'll pick this one. Then I press my shift key. Then I press my down arrow key so that I select all the cells all the way down. All the way down to the last cell. Should be cell 527. There. Then I release like that. So I don't need to do anything, but sometimes we may want to look at the residual plots. I hope we are there.
Yes.
Or you may want to check the residuals. You may want the system to generate the residuals for you. Those are the error terms to generate the residuals for you, and possibly the residual plot, so that you check whether some of the key assumptions, like that one of homoscedasticity and the one of having no correlation, has been satisfied or not. Then you just say okay. You don't have to say these two, but just check them. Then you say okay. You say okay. It takes a few seconds to process the results, and here we are. So the results are here. So even those who are doing a research project and you want to perform regression analysis, basically that is what you will do, nothing more. So we are saying that this is your beta naught and beta 1. Beta 1. So what we are attempting to do here, we are attempting to obtain these values manually. You see these ones have been computed here by Excel. So we want to obtain this manually using the formula that we've discussed today. And that's why I gave you these summary statistics from that data. The mean of variable Y is this, the mean of variable X is that. Standard deviation for the two variables, the sample size is 526, and then the covariance of X and Y is 4.15. So using this information, are you able to get these results? Are you able to get these results? And that's your task for today. That's your task for today. And I want that to be the end of today's class if there's no question.